Hello everyone. Today we are going to learn about memory management. Here are the contents in this PowerPoint. Introduction to memory management. We'll see what a linked list is, and we'll also see memory regions, which are heap and stack. Introduction to memory management. When we are doing some programming with higher level languages, we also have some advantages like the burden of dealing with many low level resource allocation issues are given apart because the programming language will handle all those issues. Issues such as assigning variables to registers or memory locations, allocating and freeing memory for dynamic data structures, etc., all detract the programmer from the task at hand. Higher level languages like Java remove many of these troublesome worries and provide high level abstract methods that the programmer can use. Here in the image, you can look at the available process address space or the memory that Java process is going to use. Java heap, native memory for Java interface, Java virtual machine, and the space taken up by the Java compiler, which is just-in-time JIT compiler, and the shared libraries, and obviously the operating system kernel. This is just a map of what memory is used by Java process. Let's recall two methods that we use in our list: add and insert at a particular location, which means insert at a given index. Inserting at a given index, inserting an element at a given index is always different from inserting an element at the end, which is easier, but inserting in middle of the list or array can sometimes require making room by shifting higher indexed items. For array lists with thousands of elements, a single call to add or remove can require thousands of instructions, which will make the program a little slower or sometimes even much slower, considering the amount of instructions that the program has or the amount of data that the array is going to hold. Let's see what a linked list is. It's a data structure which can change during execution. So with linked list, it's easier to add or delete elements in between the list of elements we have. A linked list has successive elements connected by pointers. A pointer is just a memory reference of its next node. A node or element is basically one and the same. Last element points to null because it's the end of the list. It can grow or shrink in size during execution of a program. If you want to add or delete elements, you can do that easily. Easily means you don't have to take a lot of time for it. It can be made just as long as required. As I've said earlier, you can add elements whenever you want, and memory management is comparatively better to when we compare it to the array. Here is an example of a linked list where you have the head pointing to the first node and the element A is pointing to B, and then B is pointing to C, and since C is the end of the node, it's not pointing anything. The next value here in the C node is null. Anatomy of a linked list. A linked list has a sequence of nodes. Each node contains a value. It could be a string or a number. It could be anything. And the value is inside a node, and also the next pointer's value is also saved within this node. The last node contains a null because that's the end of the link. The list may or may not have a header. As we can see here, there's no header, and in the previous slide we have a linked list with a header. Let's look at some terminology that we use in a linked list. A node successor is the next node in the sequence. B is the successor of A, and B is also a predecessor to the next node, which is C. The first node has no predecessor, and the last node C has no successor. And linked list can be empty or contain no elements, and the length of the linked list can be the number of elements in the linked list. Let's see the illustration of insertion of a new element in the linked list. Let's say we want to add this element X between A and B. What we do is we copy the link here in the A and change it to the X point. We want to make the pointer towards X, so we change A's next pointer to X, and we add the B's reference into the X's next value. So now when we have finished the operation of insertion, A will point to X and X will point to B. This is how insertion could be done. Let's see the illustration for deletion. Sometimes deletion could be a little tricky because we have to reach the node we want to delete. So we just go one by one through the list until we find the node we want to delete. Let's say we want to delete the node B. We have to go only forward because we cannot traverse back in a linked list. Of course, you can do that if you have a doubly linked list. Here we see the case of a singly linked list where we can only move in one direction, or in this towards the right side. Let's say we want to delete the node B, so we traverse this linked list until we find the current node's next is the node that we want to delete, and we find out the successor of B, and we will try to change the link in the B's predecessor, delete B's reference, and copy the reference of B's successor into A. Here we are copying A's memory location or reference into A, thereby we are deleting this reference, and this link will no longer be accessed, and we can remove this, or we can free up this memory, thereby saving us some memory space. Array versus linked list. These are some suitable scenarios where we can use arrays. Inserting and deleting element. At the end, we have more such operations: randomly accessing the elements, searching the list for a particular value. Let's see some suitable scenarios for using the linked list. As I said, inserting and deleting are much more efficient than an array. So applications where sequential access is required, or in situations where you do not know the number of elements in the list beforehand, so we will keep on adding the items in the linked list whenever we want to. These are some advantages of linked lists.